Hi everybody, Sual Pozel here. I've been getting several different requests about using simulation mechanical in the medical industry. I have a pretty active customer in Europe that actually utilizes simulation mechanical side by side with Maya to do some dental work. So here are some of the images that I received from his company, and you know, they do some basic static stress analyses and create these different stress and deformation type of plots. And I have a lot of different thesis papers around that same subject as well. In the past 2 days, I received yet another one of these requests from another firm, and this last question was a little bit different, so I wanted to demonstrate how we can solve such problems using simulation mechanical. So here they sent me an STL file of the entire mouth with implants on every teeth, but to make the demonstration a little bit quicker, I took a single implant so I can show you the workflow. Here we have an STL file that the customer sent me, and I'm just taking it into simulation mechanical to show you what that looks like. And in about 15 seconds, the STL file opens up, and we can get into the simulation mechanical interface for static stress. So here, we're looking at the STL file as sent by the customer, and I can immediately see some issues with the STL file and how simulation mechanical opens it. And it is not a good candidate for solid meshing and analysis. And as you can see, the element type is not a solid object like a brick or a tetrahedron. It was automatically recognized as a plate object. So at this point, we're at a standstill. We have to fix the mesh. And to do that, I recommend using Meshmixer. So here we have Meshmixer, and I'll go ahead and open this STL file directly in Meshmixer. So for those of you who haven't used Meshmixer, it's a free tool that you can download from Autodesk. And it's pretty neat. You can immediately view the model you have imported in the mesh view. So you can see that we have really large triangles here versus really small ones. And what I want to do is fix all these problem areas, and all the red and blue points you see are the problems. So it has a pretty quick analysis tool. You can use the inspector, and it shows you all the problem regions. And it has an auto repair tool. Once I finish the auto repair, I'm done. But I want to do one more change, which is convert this to a solid and get a more uniform looking surface mesh. So to do that, I go to the edit and click the make solid option. And it automatically creates the tetrahedral mesh that's more uniform. And as you can see, it is much better looking. And I can make it less dense or more dense, and make it more accurate or less accurate. So for this demo, I made it pretty coarse. And when I'm done, I can hit accept, delete the original STL, keep the solid STL, and do a save. And once I've saved it, I can do a save as. Oh, I can do an export rather as a new STL file, and we'll just call it new. All right. Once I have my new STL, I can minimize that guy, get out of the original, and import the new STL into simulation mechanical. Now, because this is coarse, instead of 10 seconds or 15 seconds, it only took 2 seconds to open this one. And now I have my much better looking problem-free model that I can make it a brick object or TET object. And in this case, I think I want to make it a TET object because the surface mesh is a TET mesh. And after I change the element type, I can change how I create the solid mesh by selecting the part that I've imported and create the solid mesh as a TET, hit OK, and mesh. here we have some mesh information about how many elements it created in terms of solid meshing this object. And I can make it a stainless steel, for example. And I'm ready to add loads and boundary conditions and run this analysis. So I'm just going to check instead of adding loads and boundary conditions, just to show you the solid mesh in the results environment. And here we are in the results environment. It has been solid meshed, and I can add things like slice planes to see what's happening on the inside. So let's add one, for example, in the YZ plane. So you can see the inside with the projections of the mesh. And you can transpose it to see additional details. So I just wanted to share this workflow with everybody who's interested in working with STL files more effectively. Thanks for watching.